Hello and welcome to the Virtual Student Symposium 2020. My name is Elizabeth Martinez, and I will be presenting my research thus far as a postbac in E1. This is a small overview of my research from what I began with to what I am working on to improve. So, why lattice structures and what are they? Lattice structures can be thought of as an organization of structures made from a parent material such that where there is a given strut length, the relative density varies along with the increase or decrease in the strut diameter. Since these struts can be modeled as beam elements, as a baseline model and study, I constructed a cantilever beam and analyzed it using Abacus CAE software. In these figures, I show my cantilever beam undergoing a prescribed endpoint deflection in the negative y direction. Notice how there is bending and stretching behavior in this element. I then compared my numerical analysis in Figure 2a to the ODB file, which are the extracted results from my model in Figure 2b. The model agrees well enough to my numerical analysis. The next step up was analyzing an isotruss lattice cell with the properties of titanium-64, with an applied displacement in the positive x-axis and extrapolated the force versus displacement data. All Abacus models herein use the material properties of titanium-64. Then, the next step up from that was analyzing a 2x2x2 lattice cell with plates. Having applied a displacement in the positive y-axis, I extrapolated a stress versus strain curve. The whole idea up until this point was to develop small-scale models to not only model quasi-static conditions, but demonstrate data that lies in the linear elastic regime, as shown in Figure 4c. The numerical analysis that will be used to proceed in simulating these more developed lattice structures follow the work of Mark Messner et al. In Wave Propagation in Equivalent Continuums Representing Truss Lattice Materials. As shown above, Messner mathematically obtained an effective elastic stiffness matrix for an octet truss lattice. For an octet lattice that is subjected to a displacement in the y-axis, the effective stiffness modulus simplifies to C equals E, the Young's modulus of the material, times rho bar, the relative density of the lattice, all divided by 6. Now, in comparison to the actual relative density of the lattice to the Abacus model of the lattice, the data is shown in Figure 5c, with their respective relative density in percent and kilograms over meters cubed, and calculated effective Young's modulus. In this slide, I am showing my most updated findings in a 10% relative density octet conforming unit lattice cell. And what is shown here is a continuum model, similar to that of Messner's et al. Unit lattice cell approach, where the outer struts are cut in half such that symmetrical boundary conditions are applied to these faces. In essence, this model will act as if there are octet unit cells of the same size and relative density extending infinitely outwards from the faces in the positive and negative X, Y, and Z directions. In addition, to comply with demonstrating a continuum model, TET elements were used to create the mesh. In Figure 6C, a stress versus strain curve was extracted from the data gathered from the ODB field output. As you can see, this data is representative of the linear elastic regime for this particular octet unit lattice cell. Thus, an elastic modulus was obtained from the slope of this data. Furthermore, it is observed that the results do not yet particularly agree. Efforts are being made to demonstrate a better model that is illustrative of not only numerical and analytical agreement, but also numerical and experimental behavior. The calculated effective Young's moduli for varying octet relative densities are plotted in the Ashby chart in Figure 9. Once the lattice unit cell models are updated with appropriate and agreeable Young's modulus to the calculated effective modulus, these data points will be plotted on the Ashby chart to approve or disprove a uniform quadratic scaling agreement between stretch-dominated lattices, that is, the octet, and bend-dominated lattices, i.e., a rhombic dodecahedron, after a certain relative density range that is presumed to occur 30% to 40%. Although there is much to explore within my research, I am confident that I can provide insightful work to the scientific and engineering community. This has been my presentation. Thank you for watching.